Hi everyone. In this video, we will explore the stress-strain curve and learn how to extract all the essential mechanical properties or informations of the material by using this graph. We will start with the normal stress first, then talk about shear stress and tensile stress, and then examine the elastic and plastic regions in tensile stress. What is the yield point, the properties of the yield point, the fracture point, and I will show how to determine modulus of elasticity or Young modulus, percent elongations or EL percent, modulus of resilience, modulus of toughness, ductility, and ultimate tensile strength directly from this curve. Finally, we will solve a practical example using a cylindrical specimen and calculate the Young modulus, yield strength, yield strain, by using the offset method, tensile strength, elongation percent, modulus of resilience, and final sample length, and the percent reduction in area. That's percent reduction area and EL percent or elongation percent, both of them can use for find that how much the material is ductile. Okay. In this video, we want to talk about that several important properties. Means when metals experience mechanical forces, we describe the force and resulting deformations. Key properties that comes from these informations means force versus deformation or stress versus strain, are some properties such as stiffness, such as strength, such as ductility, hardness, are measuring specific parameters to quantify material behavior. Some of this information exactly comes from the tensile test, some of them another test, such as hardness properties, but there is a relation between hardness and tensile strength that in another video that we will talk about hardness test, we go deeply and explain what is the relation between hardness, such as Brinell hardness and tensile strength. Okay. Mechanical properties classified in this table, such as toughness, that is the energy that sample absorb before fracture. We will talk about that in other slide. And the test that used for measuring toughness is impact test, Charpy test, or ISO test. But some important information from tensile test gives out good scale for measuring toughness too. Talk about the modulus of resilience, means how much energy absorbed by the samples or by the structures in elastic region, means ability to return to original shape. About the hardness, or the material has this property that we say hard, resistance to indentations or surface wear. Strong means the tensile strength or the maximum stress that can tolerate before failure. Ductility, or the property is ductility, and the material has this property. We say ductile materials means ability to deform plastically without any fractures, means how much deformations or maximum epsilon tolerate or strain tolerate before fracture. And the test, we can use that definitely tensile test and tensile elongations or reduction of the area. Both of them can use as a good scales for measuring ductility of the material. Brittleness, and the material have this property, we say brittle, means low plastic deformation or low epsilon F, and we use tensile test, low EL% or elongation percent is a good scale or good criteria for measuring brittleness. Okay. Simple tensions occur when the materials is pulled along one axis, and this force is produce normal stress, and force is perpendicular to cross-section area, as you see here. This cross-section area is this, and force is this, and you see that it is perpendicular. Okay. And this equation, we use F per A naught, and we talk about that in next slide, that it is not through stress or through normal stress. It is engineering stress. Anyhow, we have two types of the stress, normal stress and shear stress. In normal, force perpendicular to cross sections, and normal, we can say tensile or compression, and here is tensile, means comes to outside of the surface, means the length will increase or under extension. Okay. Torsion. Torsion happens when material is twist about axis. This generates shear stress that we show by tau, and this varies with the radius of the structure. So, as you see here, is a function of R, yeah? Is function of radius of the structure, for example, for cylindrical shaft or something. Okay? Compression, as I told, normal stress classified in tensile and compression or compressive. It is tensile and it is compressive, means inside the structures, and the length will decrease that. Again, we use the same equations, but if the sign of sigma be positive, means tensile, and if be negative, means compressive. Okay, the stress strain test is very important test for measuring many mechanical properties. Today we want to talk about that. Stress strain test measures how material deform under the load. It provides key properties such as Young modulus, yield point, yield strength, yield strain, tensile strength, toughness, resilience, and fracture behavior, plastic region, elastic region. Many information we can derive by doing this test. Engineering stress. Engineering stress is calculated using the original cross-section area or initial cross-section area, such as A naught that you see here. You know that when the structure is under loading, definitely this cross-section is not fixed and constant, means changing by time. So if we put the real A or instantaneous A, definitely sigma be more accurate, that we say true stress for that. Here we have shear force that parallel to cross-section area. Again, tau, this engineering tau or shear stress, if we divide force per A naught or original cross-section area or initial one. Engineering strain. You know that the average of del epsilon is delta L per L naught, yeah? So if we use L naught and deformation in each time divide per L naught or initial length, it is engineering strain. It is for tensile strengths that you see here, but you see that in other directions we have decreasing the amount of that you see minus this minus because of that. and shear strain we show by gamma. What is the difference between shear strain and normal strain? Normal strain related the increase of the length, but shear strain is about the change of the angle. For example, you consider the sample or cross section was in this form before applying any shear stress. After applying shear stress, the angle will be this. How much change? For example, first was 90, now is, for example, something's alpha. How much change? The change of that, we say theta, and theta in this triangle, tangent theta is delta x per y, yeah? And we say this tangent theta as gamma or shear strain. So shear strain is change in the angle of the cross-section area. But tensile strain or for normal strain, it's better say that, means change in the length or diameters, means lateral or axial strain. Okay. There is a useful linear elastic relationship that only valid and works when we are in elastic region for tensile. Okay, that say delta L is F or summations F or depends to the free body diagram at that cross section times L naught per E A naught. And you see that when we have extension in one side, we have a decrease in the area or another directions or lateral one, and you see minus nu. So deflection depend on the material, geometric and loading parameters, and material with large elastic modulus deform less. Why? Because when E increase, definitely it is in denominator of this fraction, delta L decrease. And it comes from the Hooke's law that in next slide, we will talk about that. Okay. The relation between stress and strain in elastic region is completely linear. The name of this equation is Hooke's law, and sigma or normal stress is E Young modulus times normal strain. Okay, if you remember, sigma was force or P or F divided A naught is E, and epsilon is delta L per L naught. So we can derive this equation that delta L is PL naught per A naught E. And it is the equation that we saw in previous slide that it only works for elastic region. And here you see some unit for that, unit for E in gigapascal or PSI, and 1 gigapascal is 10 to 9 Pascal. What is Poisson ratio? Poisson ratio is the ratio of the lateral to axial strain in a material under loading. It characterizes how material deforms sideways, and it measures using a strain gauge or extensometer under tension or compression or under tensile test. And you see several nu for metals, approximately 0.33, ceramic 0.25, polymer 0.4, and the equations for that is minus epsilon z per epsilon x. If the force applied in x directions means it is the axial strain, and here it is lateral one. Okay. Other elastic properties such as shear modulus G, bulk modulus K, and the relation between E, G, nu, or E, nu, and K. What is shear modulus? Shear modulus is G, as same as Hooke's law that we have between normal stress, normal strain. We have between shear stress and shear strain, tau shear stress, gamma shear strain, and in elastic region, they relate to each other as tau equals G gamma. What is bulk modulus or K? Describe resistance to volume change is minus K delta V per V naught. What is delta V? Change in volume, and V naught is initial volume when applying hydrostatic pressures in same all directions and same amounts, means hydrostatic pressure. And this P is minus K delta V per V naught, and we call that bulk modulus. The relationship between E, G, and nu and E, nu and K only for isotropic materials, means homogeneous in all directions properties. Use these equations. What is plastic deformations? Plastic deformation is some permanent and irreversible deformation. For example, you consider we are at stage 1 first, initial, then applying force. Some deformation you see in the structure that is delta L elastic plus delta L plastic. And you see that bonds stretch, atom displaced, and they are a slip system. You see the black lines. Anyhow, in stage 3, when we remove the force, means elastic deformation recover, means back, but some deformation permanently be in the sample and is irreversible. And okay. Plastic deformation stress strain plot. You see that when we apply force here, we are in elastic region. After yield point, that somehow maybe in this point, we enter to plastic region, means the this curve is not linear more, and it's completely non-linear, the relation between stress and strain. When we remove the remove the force, you see that recovery completely parallel to linear part or elastic part and reach to this. This epsilon or permanent epsilon is the permanent strain that irreversible and will be in the structures, and we cannot do anything for that. Yeah, there are some ways, means applying force in another directions that remove this, but today we will not talk about that. Means if we apply stress in another direction, finally a strain will be 0, but we have some stress in the sample structures. Okay. Yield strength is very important point for us, means transition from elastic to plastic region is gradually, sometimes we cannot exactly specify that what is the yield point. We need some techniques or some methods for finding this point. One of them is offset method. What is offset method? So it is elastic region and it is plastic, yeah? And we don't know, and starts of plastic. And we don't know where is the, after that is plastic. Where is the yield point exactly? What should we do? We specify epsilon p 0.002 and draw a line completely parallel to linear part. Intersect with, for example, you consider it is the continuum of stress strain curve. Intersect to the curve at this point. This point is yield point. The stress of this point is yield stress. And strain of this point is yield strain. Means if we have a strain more than this, literally means that we enter to plastic region. Okay. What is tensile strength? Tensile strength is the maximum stress that structures experience under loading. For metals, usually it occurs at the beginning of the necking. What's the meaning of necking? Means that we expect that the stress increase up to fractures, but for the metals, we see that at stress so considerable, less than maximum, if we say it is sigma max or tensile strength, fracture point is here. So sigma F is lower than this. So this phenomena after maximum, this part we say necking occurs. Ductility is the property that measures the plastic deformation before the failure. It is specified by percent elongations and percent reduction area that you see the equations. EL percent means LF. LF means final length or fracture length exactly before fracture. Minus L naught or initial length, divide L naught times 100%. And RA percent means A naught minus AF or fracture area, cross-section area, where A naught again, initial cross-section area times 100%. Okay, back here. You see that epsilon F is so lower than this. So the green one is more ductile compared to blue one, and blue one is more brittle. Modulus of resilience is the material's property to absorb energy in the elastic regions and return it upon unloading. It is represented by the area under elastic portions of the stress-strain curve. Means that if we know sigma y, look at here, it is approximations. We cannot say exactly this, but if you see the difference I show. For example, here, you see the area, it's not exactly triangle. There are some difference, yeah? But approximately, if we consider the triangle, the area of triangle is height times base divided by 2. Means height is sigma y, base is epsilon y divide 2, and it is not exactly y because there is a difference between this area. I can show you the difference is shown by green color, okay? Toughness is the material's ability to absorb energy up to fractures. It is represented by the total area under stress, strain curve. And you see that, for example, as for the pink one, very small, for the green one, large toughness, such as metals, and blue one, small toughness, such as ceramic, for example. True stress and engineering stress, true strain and engineering strain. We talk about that, that it is more accurate if we want to have insight to the properties, but definitely measuring that is difficult for us. For example, when we are doing the test, we cannot always use the length at that time in our equations for the epsilon, or for example, use a cross-section area exactly at that time. Because of that, we use engineering, but definitely if we use the true stress and true strain, is more accurate. So T here is an abbreviation or symbol of the true, is F per AI. What is AI? Means instantaneous cross-section area. And epsilon, as you know, is the integral of dl per L between L naught and L at each time, yeah? That I show, for example, is Li. This integral is ln L between L naught and Li, so it should be ln Li minus Ln L naught that convert to this equation. So what is Li? Means length exactly at the time that we want to calculate or derive the strain at that time. Okay, there is a relation between true stress and engineering stress. They relate to each other by using this equation. And there is a relationship exactly between true strain and engineering strain by this equation. Okay, elastic strain recovery is the material's ability to return its original shape after the loading is removed, but only the plastic portion of deformation is recovered. I talk about that. The slope of this line completely same as the linear part or elastic part, so they are parallel to each other. Some deformation, this part recovered, but this part be epsilon p or permanent strain that be in the structures forever. Okay. Polymers exhibit unique stress-strain behavior, often showing a large elastic deformation. Most of the polymers, this, for example, is here, how much we have is about 780%. For example, here is about 410%. Is considerable compared to such as metal or some things. For example, for metals, we have 10%, 15%, some things means epsilon F or fracture strain or the maximum deformations that we have. So polymers show large elastic deformation and significant plastic flow. Their mechanical properties depend on molecular structure, temperature, strain rate, and some things. Okay, one thing that's very important in designing is design safety factor. The design safety factor are used to ensure engineers that structures and components operate safely under unexpected loads. For example, we know the yield strain in a structures or in a material, and we want design structures that n times be safe, means allowable stress should be sigma y divide n. Sigma y is yield strength, it depends. Sometimes maybe ask that tensile strength by considering that not only being elastic region, means being in plastic no matter for us, but only not fail. So we consider sigma max or tensile strength divide n. It depends that in which criteria we are designing. Okay. For example, here we have the cylindrical rod to be constructed from steel. Yield strength is 310 megapascal, is withstand a load of 220,000 Newton without yielding. So here we want design a structure or component that not reach to yielding point or not enter to plastic region. Assuming a value of safety factor n equals 4, specify suitable diameters for this bar. So sigma allowable or W, sigma y divide n. Sigma allowable is force divide per cross-section area. Sigma y, we know that it depends on the material property that is still 310 megapascals and n is 4. By substituting that, D should be minimum, 60 millimeters. Means if D more than this is completely safe, but shouldn't be less than this if we are looking for safety factor 4, okay? And finally, we want to derive all informations that today we talk about that by having the graph and derive all the information. Okay, using the stress strain curve for the steel alloy showing this figure, along with the two zoom in sections in Fig B and C, answer the following. The specimen cylindrical with the following dimensions. Initial diameters 12.8 to 2 millimeters. Fracture diameters is 8.704 millimeters. Initial length is 51.07 millimeters. Okay, at part A, determine the modulus of elasticity. Show this on the graph. If you look at here, modulus of or Young modulus is the slope of this line, the slope of elastic region. Okay, so if you consider this triangle, tangent theta is what means this, that, so E is other side means 200 minus 0 divide per another adjacent side that, for example, 0.01 minus 0, yeah? And should be, for example, 200, sorry, it is another 0, times 10 to 3 megapascal or 200 gigapascal, okay? The next part, find the yield strength using the offset method. For yield point, I told that we considered or increase the strength for all points 0.02 and draw a line parallel to linear part. Means the slope of this line is 210 to 9 or 200 gigapascal. They intersect the graph at this point. This point, the stress is 400 megapascals. And if I change the color and yield, so it is sigma y, and it is yield point. And epsilon y is 0.0037, for example. Next, determine the tensile strength and mark the corresponding point on the graph. Maximum stress is the tensile strength, or sigma max, that is 515 megapascal. Okay? D, identify the fracture point. Fracture point definitely is the end point at the graph, so it is fracture. The sigma is 375 and strain of the fracture, or epsilon F, is 0.187, okay? E, calculate the percentage elongations and indicate this on the graph. Okay, as you know, epsilon L or EL percent is LF minus L naught per L naught, or epsilon F, yeah? So it should be 18.7% for this problem. At the next part, calculate the modulus of resilience. Okay, for calculate them, or UR, we have three equations, or we can use three forms. Half sigma y times epsilon y, or sigma y squared per 2e, half e epsilon y squared, and all of them same. It depends that which information you have. If you have sigma y only, use the second one, for example. If you have epsilon y, use the third one. If you have both of them, you can use, but I preferred for this problem, for example, use sigma, only use this one, because sigma y is 200 megapascal as is round number, whole number is better for me. Okay, and if we want show the area, it is the yield point. So the area should be something as same as this. And it is 0.4 megapascals. Megapascal maybe for energy not makes sense, but pascals is Newton meter squared. We can multiply meter per meter. So it should be joule per meter cube. So now it makes sense. Means energy per volume. Okay, the next part asks about the fracture length. You know that EL is LF minus L naught times 100. And LF is L naught times 1 plus epsilon F. We have epsilon F, we have initial length, substitute here, and we can find fracture length as 60.62 millimeter, for example, for this example. And the next one asks about RA percent or reduction area percent, means A naught minus AF per A naught times 100. It is circular cross section, so pi d squared, d naught squared per 4 minus pi df squared per 4, again divide A naught. If you substitute initial diameters and fracture diameter in this equation, we reach to reductions of area of 53.92%. Okay, thanks for watching this video. If you are interested to having the PDF of the video, please follow the descriptions of the video at the YouTube. Thank you so much. Bye-bye.